Hello everyone, welcome to the GATE NPTEL lecture course. Today we are going to solve question number 45 from GATE 2015 question paper. So in this question it is given that a long solenoid is embedded in a conducting medium and is insulated from the medium. If the current through the solenoid is increased at a constant rate, the induced current in the medium as a function of radial distance r from the axis of the solenoid is proportional to. So basically, we have given that the current is increased at a constant rate. So del I by del T is increasing at a constant rate in the solenoid. So for the sake of simplicity, I am drawing the solenoid here as a simple cylinder, and where the current is flowing such that the magnetic field is in the z cap direction. So basically, current is flowing like that, and this is the direct axis of the solenoid. So the magnetic field due to a current I carrying atoms per unit length is given by mu naught n I in the z cap direction inside the solenoid, and it is zero outside the solenoid. So we have to find out how the induced current will vary as a function of R. Now, due to the change in this current, there is a change in the magnetic field, and it is known from Faraday's law. Whenever there is a change in magnetic field, electric field also going to induces, and which is given by this Maxwell third equation that curl of E is equals to minus del B by del T. Now this change in electric field is account for the EMF in the system, and since current I is equals to EMF upon resistance, therefore by knowing how our electric field is vary as a function of R, we can find out how our induced current is vary as a function of R. So if I take the surface integral of this equation, surface integral of curl of A dot dA vector is equals to minus surface integral of del P by del T into dA vector. And by applying Stokes' theorem, we are close integral of E dot dl vector is equals to minus surface integral. So now we know what is our magnetic field due to this solenoid, and in cylindrical coordinate dA vector is given by r t r t phi in the z cap. Here dl vector, if you are talking about here, we have taken an imperial loop inside this solenoid of radius r. First is the case when we wanted to know how the field is very inside the solenoid. So we take the imperial loop inside the solenoid. So in this case, the dl vector is along this imperial loop. So dl vector here is in the phi cap direction. So it is r d phi in the phi cap. So by doing this, our electric field E dot dl is comes out to be E into phi will vary from 0 to 2 pi r t phi equals to minus surface integral of del phi by del p is mu naught ni. dA is r t phi. So basically r is vary from 0 to r inside and phi is vary from 0 to 2 pi. These two are constant with respect to 3, so only del I del T will be left here. So we are left with mu naught I 2 pi r equals to minus mu naught n I del I by del T 2 pi r square by 2. So we calculate 2 pi r is cancel out. Oh, there is 2 left. 1 r is gone. So magnitude of E is minus 1 by 2 r mu naught n del I by del T is constant. It is vary at a constant rate. So these quantity are all constant. So magnitude of E field vary as a function of R as we are considering the inside case. Now let us consider the outside case. In the outside case, the only thing that is changed is we have to take the imperial loop outside, but the magnetic field is inside, non-zero inside, outside it is 0. So the radius of this outside loop now taken as R. So in the case of outside, when we try to calculate close integral of mod E vector dot dl, it is again mod E outside 0 to 2 pi RT phi. So basically mod E to pi R. And the right hand side, which is minus surface integral of del B by del T into dA, which is minus 0 to R, 0 to 2 pi del by del T of mu naught N I dA R T R T phi. So basically this field mu naught Ni is valid as long as we are talking about inside radius. Outside it is 0. So basically 0 to R it is finite, but R2 small r 0 to 2 pi, all these quantity will become 0. So this is integral becomes 0. So here this quantity will become minus 0 to r 0 to 2 pi 0 to r del by del t of mu naught n I r t r d phi. So when we integrate it, we'll be left with mu naught n del I by del t r square by 2 into 2 pi. So when we put a left hand side equals to mod into 2 pi r equals to minus mu naught and del I by del t r square by 2 into 2 pi. So 2 pi will cancel out and our E field will become minus del I by del t is scale, it's a constant. So mu naught and r square by 2r. So this is the outside field. So outside field E is vary as a function of 1 by R. However, inside field is vary as a function of R. So the correct answer is the induced current, which is proportional to the electric field, is vary as a function of R inside the solenoid and 1 by R as a function of outside. So the correct answer is D. This is the correct option here.